This is data-only Pwning Microsoft Windows kernel, exploitation of kernel pool overflows on Microsoft Windows 8.1 with Nikita Tarakanov.
Thank you very much, Alan. So, hello everyone. Thank you for joining this talk. So I'm gonna talk about exploiting pool overflows on the Microsoft Windows kernel, and with like long title, right? Data only Pwning. But in the end of the talk, you will understand why the title contains data only Pwning. So we're gonna like briefly introduce why pool overflows. Next I'm gonna talk about some very basics of pool. Also cover previous research in that area, new idea, mitigations, and question and answer section. So talking about kernel, especially pool overflows, like if we take a look how like system get compromised, the first step is like so-called drive-by download. For example, you surfing some website that is that contains like exploit pack, and the attacker get execution, but in ring 3, and nowadays in sandbox. So attacking from sandbox kernel is nice idea. So you get you like escape sandbox and get code execution in kernel, and it's pretty nice. And nice examples compromise of Internet Explorer this year, Pwning, and last year. So yeah, following like 5 slides, it's very basics, and if you want to know like deep details about how pool works, check work by Tarjimant. He did a lot of research on that subject. So basically, pool header defines like chunk of memory. It contains several fields like previous size, pool index, block size, pool tab, pool tag, and on 64 bits it differs a little bit because it contains a pointer to eProcess structure. So if the chunk is freed, after pool header there is a list. There are 2 pointers. Basically, it's link entry structure, like pointer to forward chunk and to previous free chunk. Also, it's nice to know how allocation takes place. First allocation comes in the top, and second and following from the bottom. And also, to avoid fragmenting, there is a algorithm to merge adjacent free chunk. For example, if you have like situation like on that picture, for example, you have 2 chunks and one is busy but is going to be freed. In the end, kernel makes one big free chunk. So as I already said, talking about attacks and exploiting pool overflows, there are 2 ways. It's corrupting pool metadata and corrupting not pool metadata, for example, object metadata. And talking about pool metadata corruption, there are a lot of techniques, mostly discovered by Tarji. But the thing is, if we take a look that on Windows 7, he discovered a lot of techniques. On Windows 8, Microsoft eliminated almost every technique, and on Windows 8.1, it's even more hard to exploit pool overflows using pool metadata corruption techniques. So let's take a look briefly on object metadata corruption. So when you create some object, like for example file, using create file, event, semaphore, Object Manager creates object. Of course, it uses some pool memory, so there is a pool header, but pool header is just container. And following is optional headers. Depending on type of object, there could be several. And after optional headers, there's object header, and after object's body. So talking about object header, in object header there is very interesting field, which is type index, which is basically unsigned char or byte, and it's indexed in the array of pointers, and these pointers are basically object types, and they define object type. This debug print is for Windows 7, for Windows 8, because on Windows 8.1 it looks a little bit different. So that structure object type contains another structure, and this structure contains an array of function pointers. So the thing is that if you, like, for example, closing object, depending on the type of object, object manager will call a specific routine to close the object, to delete like dynamic memory that was allocated on when the object was created. So basically it looks like that. There is a type index, there are an array of pointers to real object type, and object type contains a function pointer that will be called. So before Windows 8.1, if you take a look, that first elements, first is 0 and the second one is some magic constant beta bobo. So, and on 64 bits, beta bobo is extended by zeros. So basically, that kind of magical value is it's memory that resides in user mode address space. So the thing is that attacker can simply, before Windows 8.1, can simply smash type index with 0 or 1 value, allocate fake object type at 0 address or beta bobo, and redirect and hijack execution flow. So on Windows 8.1, Microsoft didn't change first element, because on 8 and on 8.1 you can't allocate at 0 address, but second element they changed it to address, and actually this address they in the very early booting process of Windows, when Object Manager creates object types, it allocates memory. So for user mode attacker, there is no possibility to somehow alter that memory. So there is no way to inject memory there. So this attack using like beta bobo and type index 1 was simply eliminated. So the thing is, I thought, okay, if that array of type index table doesn't contain any special values, so what about like changing, like smashing object body, or looking to how we can change type index to different one, and look for benefits. For example, the first one was type confusion. So what happens if we change type index from one legitimate to another? So basically we leverage Pool Overflow to type confusion, and after smashing type index, after making type confusion, after smashing object's data, we access this like malicious overwritten object, and that gives to attacker a lot of primitives. So basically, after overflow, object header using type index for object manager, after Pool Overflow, it looks that it's different object. So we can use like different system services to access that object. So there are a lot of scenarios, because as you saw, there are several function pointers and object type initializer structure, but in fact you can like access object using various system services, So talking about type confusion and changing execution flow from one legitimate to another, for example, there is a print of function pointers of directory object. As you can see, like for example, security procedure is a SE default object method function. And if we take a look at file or device object type, security procedure is a different one. So, for example, if we spray a pool with event objects, object type of event contains security procedure initialized as default object method. After corruption, we change type index to file object. So we redirect execution flow from default object method to IOP get set security object. So object manager works with file object, but in fact it was event. And it leads to, basically, in that scenario, in changing to file object, it leads to hijack of execution flow. But in fact, there are different ones. Unfortunately, this security procedure, almost every object type contains function just as default object method, and it's not very useful in exploitation terms. But IOP get set security object is very nice because there is a triple dereference of file object, and basically that leads that you control EIP or RIP. So it looks like basically here are 3 dereferences. We get one pointer from our smashed object, so we control pointer, we can craft our fake device and driver object in the user mode memory. And in the end, it will jump to our ROP chain or shellcode. So I cut these structures because device and file object, they are bigger, but the most important is just pointers, like chain. And driver object in the end, it contains a mayor function array, which basically function pointers. Talking about other procedures, like for example, when you call close handle and object manager calls close and delete procedures, these are a lot of ways, because almost every object type has a specific close and delete procedure. So there are 56 functions, so 56 execution flows, mostly lead to arbitrary memory override, some to adjacent read-write, and some to hijack of execution flow. For example, talking about key object type, it's one of the most powerful object type for exploitation. For example, CMP security method, it also leads to hijack of execution flow, and also to different primitives like write and read. So also there are 7 of them, plus like close, secure, delete, and this like 5, so yeah, 8 in the end. But unfortunately, not a lot of object types contain initialized like these function pointers. So there is not a lot of interest in here. Also, objects, it's like they have typical OOP interfaces. For example, constructor, like create file, create event, create semaphore. Destructor is one, it's just close handle or entity close. There is also getter and setter, and a lot of type-specific system services. But unfortunately, you know, my idea was, okay, this is very nice, so you can just change object type to different and like find system service that read or write memory. But unfortunately, object type has a field valid access mask, so you cannot freely use this way of accessing smashed object, because you have to find object types that have same valid access mask, or just don't change type, so don't use type confusion, just object data corruption. But the good thing that some object types they do have same valid access mask, so you can play with that. For example, talking about like getter and setter. Getter mostly good for arbitrary read primitives, for example, symbolic click object. This object contains a Unicode string, and Unicode string contains buffer, and max and size is maximum to maximum word, so FFF bytes. So this primitive gives you reading of arbitrary memory. Also, for example, query directory object. This object contains like an array of object headers, so you can craft up to 25 like malicious object headers, and basically it leads to 25 in hex, so 37 times of reading arbitrary memory using just one system service. Also, for example, query information worker factory, it leads to arbitrary memory read, but just for like 8 bytes, right? Or for example, setter, it leads to arbitrary write primitives. For example, talking about this system service, it leads that just by smashing one object, it leads to infinite amount of overwriting arbitrary memory with controlled values. It's pretty nice. So just one smashed worker factory object, and you can write to memory what like infinite amount of times. So I thought, like, you know, in fact, on this stage, when you hijack execution flow, most of you like say, okay, but it's already done. But I thought, like on Windows 8, like with SMEP, you have to like redirect to rob chain to disable SMEP, or call xallocate pool with stack with executable memory, then copy your shellcode, execute it. So, you know, like I thought maybe if you have so amount of primitives like arbitrary write, arbitrary read, there is no point to hijack execution flow if typical payload of elevation of privilege exploits in Windows is just a copy token of system process to attacker's one or to current one. So basically it's just copying data from memory A to memory B. So it's just, in fact, it's just one instruction, right? Move memory from A to B. So I thought when you have this, like these primitives, reading, writing, you can emulate typical shellcode. For example, when you're looking eProcess by process ID, it's just parsing of one structure that resides in memory. And using read primitive, you can parse the structure, and using write primitive, you can copy token, system token. So in fact, there is no point in execution shellcode using ROP. You just can use an absolute legitimate code like here or here, but with corrupted context of object. You simply make your payload with legitimate code, and it's not ROP, it's not your shell code. So, in fact, why it's good? Because if you redirect your execution flow to ROP, and if on target there is some hypervisor like I don't know, like Bromium, vSentry, or Deep Safe, or McAfee Deep Safe, it can like detect it. For example, if your ROP payload, ROP chain disables SMAP, it disabling SMEP, like changing bits in CR4 triggers VM exit. So some HIPS that works in hypervisor simply detects it. So, but this method, like for hypervisor and for kernel, is just triggering system services, and that's it. So it's kind of legitimate way, but because objects are corrupted, it's like you do whatever you want to do with kernel memory. So, talking about mitigations. In fact, like I can talk about hardware perspective, because with SMEP, like I bypass SMEP because I don't play with it. I don't try to disable or bypass it. Talking about SMAP, it's nice because let's like take a look. So if you can read by UN kernel and you can read memory at like in user space, here is okay. You just smash file object with pointer to user mode memory. But with SMAP, you have to craft it in kernel memory. So you have to have some ways to construct complicated structure in kernel memory. And in fact, sometimes to do that, you have to have another vulnerability. But talking about Microsoft, I think maybe like inject cookie in object header and check every access to smashed object and check cookie like same with stack canary. But in fact, in my opinion, the best way, it's what actually Microsoft did recently for user mode. It's isolated like for IE isolated heap. But what if to make same but for kernel isolated pools? So basically, it will lead that attacker will not have possibility to fragment pool into state good for exploitation. So there will be no adjacent pool header with object inside. So I think that isolated pools, and basically Microsoft already has it because there are different kind of pools, non-paged, paged, session pool. But for example, if they isolated more, like objects, like for example events will be allocated only in specific range, files only in specific different range, and etc. So in conclusion, like there are some nice quotes, and they like represent how exploitation techniques evolve. So first, it was a nice quote by Peter, like heap sprays of 99%. Follow up was by Tombkeeper. It's, return rate in programming, like is for 99%. But I thought, like talking about elevation of privilege, what if that we don't need like our payload, because everything legitimate inside. You just need to smash objects in a proper way. So that's it. Yeah, by the way, talking about pool deep details, check out Tarjay work, and about previous work on object metadata corruption, check my previous work from Hack in the Box. So, any questions? Yes? Yeah, basically when you use getter, setter, and specific, there is a code in kernel that passes pointer to object type. And if you smash the object, there will be like kernel will check if it's like valid access mask from that object, but it was smashed with, so there will be not equal. But the thing is, when you use procedures, there is no such check. So with procedures, like with this vector, with close, delete, secure, you can change object type from A to B without any restrictions. But unfortunately, this method, like using getter, setter, there is limitation. Any questions? Yeah, I speak fast. Well, basically, if it's not clear, I can explain something in detail, because the talk is like specific. No questions?